So far we have discussed the protocols in which we will try to send one frame and wait for the acknowledgement before we transmit the next frame. So we were not implementing pipelining mechanism in either stop and wait or stop and wait ARQ. But because of this, you could find the channel efficiency and bandwidth utilization was poor. To overcome that problem, we were trying to implement a process called pipelining, in which more than one frame can be sent before waiting for an acknowledgement. So to improve the efficiency of transmission, filling the pipe, multiple frames must be in transition while waiting for acknowledgement. In other words, we need to let more than one frame be outstanding to keep the channel busy while the sender is waiting for the acknowledgement. Simple. I send frame 0. Then before I wait for the acknowledgement, I can send frame 1, frame 2 so that the channel can be more occupied and it can be fully utilized. In this protocol, we can send several frames before receiving the acknowledgement. We keep a copy of these frames until the acknowledgements arrive. So though we are sending more than one frame at a time, but all the frames that are transmitted, we are keeping a copy so that until we receive a positive acknowledgement for the frames. If we receive a negative acknowledgement or if we don't receive acknowledgement for a particular frames, we are going to retransmit. So we need a sequence number to be assigned for the frames, but here the sequence numbers will be different from the stop and wait ARQ, which we discussed in the previous session. In Go Back N ARQ protocol, the sequence numbers are modulo 2 power m. So what do you mean by m here? So m refers to the size of the sequence number field in the bits. For instance, I want to use a sequence number of 3 bit size. Then m equal to 3. So totally I will have 2 power 3 8 combinations which starts from 0 and can be up to 7. Similarly, if m equal to 4, the only sequence numbers that can be used are 0 to 2 power m minus 1. So what is m here? 4. Totally 2 power m equal to 16 combinations are possible, and for that we can have a values starting from 0 to 2 power 4 minus 1, which is nothing but 15, and this sequence can repeat. Go back an automatic repeat request protocol. Here, the sender window size is an abstract concept defining an imaginary box of size 2 power m minus 1, and we will have three variables in your sender window. What are that? SF, which indicates the sequence number of the first outstanding frame, SN, which holds the sequence number that will be assigned to the next frame to be sent, and S size, which indicates the size of the sender window, which is fixed in the protocol. Now, what SF actually stands means, suppose I have already sent a frame and I am waiting for the acknowledgement. What is the first frame that I have sent which has been transmitted but yet to be acknowledged? That will be defined by the variable SF. SN indicates the sequence number that will be assigned to the next frame to be sent. Already some frames are sent, and once they are acknowledged, we are trying to send the next frame. What is the next frame that you would like to send is indicated with a sequence number SN. And S size indicates the total sender size window, which is fixed in our protocol. Now, as some of the frames which are already transmitted receives the acknowledgement, then the sender window can select one or more slots, and accordingly we will have a new value of SN and SF that we will be looking in the next slide. Let us look at the sender window for a Go Back N automatic repeat request protocol. Here we have an m equal to 4. M indicates number of bits to indicate the sequence number. So with m equal to 4, basically we can have 2 power 4 16 combinations, and sequence numbers allotted are 0 to 2 power m minus 1, which is 2 power 4 minus 1, 15. And after 15, again the sequence numbers will be repeated. And the sender window size is equal to 2 power m minus 1. So this is 2 power 4 minus 1, that is equal to 50. So the sender window size is 50. The sender window in Go Back N ARQ is divided into 4 blocks. The first one is the frames which are already sent and acknowledged. Will be the first. The second block is the frames which are sent but yet to be acknowledged. They are called as outstanding frames. So some of the frames are already transmitted to the receiver, but they are not yet received the positive acknowledgement. The next will be the block which contains frames that are to be sent. And last block represents the frames that cannot be sent until the previous frames are completed. So totally we have 4 blocks in our sender window. Now, as we communicated, the first 3 frames here are already sent and acknowledged, and 0 to 6 frames are sent to the receiver, but we are waiting for the acknowledgement. Among this 0 to 6, the first frame which is sent and yet to be received acknowledgement is frame 0, and that first frame will be indicated with a variable SF, the sender window first outstanding frame. And next block indicates the frames to be sent, and the first frame which can be sent will be referred with a variable SN. The sequence number of the frame to be sent next is 7, so SN equal to 7. Okay, and until 14 frames are sent, we cannot include 15 to be transmitted. Now, among the frames that were sent, if the frames 0, 1, 2 are acknowledged, so not only they have sent the frames, but there have been already, now they got the positive acknowledgement. So these frames which are in the outstanding frame position will be moving to the frame sent and already acknowledged. So now 13, 14, 15 we also have 0, 1, 2, the frames already acknowledged. Now the frame which is sent and expecting to get an acknowledgement starts from 3 and we have up to 6. The first frame for which we are waiting for acknowledgement is 3, so the SF will be equal to 3, and the next frame to be sent is still 7, so SN equal to 7. Now total size of window is 15, and now once 0, 1, 2 are cleared and moved out of the window, now we have the window size occupied is 3, 4, 5, 6, 4 frames which have been in outstanding plus 8 frames which are ready to be sent. So we have total occupancy of 4 plus 8, 12. So the frames to be sent 1501 now enters into the sender window. So what are the frames which are sent and acknowledged? 3, 4, 5, 6. And what are the frames to be sent? Starts from 7 and we can have a sequence number up to 1. Now let us look at the receiver window size for a Go Back N automatic request ARQ. Here the size of the window is only 1 bit. So the RN is actually trying to indicate the sequence number of the frame which is expected to receive. So here you could find there are 2 blocks, the frames already received and acknowledged and the expected frame to be received, and frames that cannot be received until the previous expected frame is received. Okay, for instance, if I have received the frame number 3 and that is acknowledged, my next expected frame to receive is 4, and now the RN value becomes 4. The receive window is an abstract concept defining an imaginary box of size 1 with one single variable RN. The window slides when a correct frame has been sent, and sliding occurs one slot at a time. Let us observe the design of the Go Back N automatic repeat request protocol. Here, once the data link layer receives the data from the network layer, it converts the data into frames. The only difference between Go Back N ARQ and Stop and Wait ARQ is here the data link layer can send more than one frame at a time before waiting for the acknowledgement. For instance, we are sending 4 frames, and the first frame out of those 4 outstanding frames will be referred with a variable SF. The next frames to be sent are indicated in white, and the first frame out of those frames to be sent next will be indicated with a variable SN. So whenever the data link layer of the sender tries to send the frames to the receiver, they keep a copy of the frames so that in case of any error, they will be retransmitting the frames, and every time a frame has been forwarded, you will find a timer has been initiated, and the sender would be expecting to receive a confirmation positive acknowledgement for the receiver before the timer expires. If not, the sender will be resending the same frames. At the receiver end, the window size is only 1, so each receiver can only receive 1 frame at a time. When a frame is received by it, it will verify if there is any error or not. If there is no error, it will extract the data and deliver the data to the network layer and send an acknowledgement. Suppose frame 1 was transmitted and received by the receiver successfully, it will extract the data and run. The next frame which is expected by the receiver is frame 2. In case frame 2 is not able to be reached and frame 3 and frame 4 are transmitted, the receiver is not ready to receive the data. And what happens is, for all the frames 2, for instance, let me put it a number, 1, 2, 3 and 4 frames are sent. 1 is successful, so it will generate an acknowledgement and will retransmit it, and 2 got corrupted. Though 3 and 4 are received successfully, yet the receiver is not ready to receive the frames 3 and 4 because the expected frame to receive after receiving the frame 1 is frame 2. So all the 3 frames 2, 3, 4 will not be able to get acknowledgement from the receiver. Hence, after the timer of 2 second frame expires, all the 3 frames 2, 3 and 4 has to be retransmitted. Though 3 and 4 are successful in reaching to the receiver, because 2 was not transmitted correctly, we have to retransmit all the frames starting from 2. Hence, this mechanism is called Go Back and Repeat ARQ. Let us understand the flow diagram of Go Back and Automatic Request Protocol. Here, initially, we would like to send a frame 0. For this, let me make you understand. For this example, we are taking the value of m equal to 3. So, number of bits to represent sequence number is 3. The possible values, total combinations available are 2 power m, which is nothing but 2 power 3. So, totally you can have 8 values starting from 0 to 2 power m minus 1, 2 cube, 8 minus 1 is 7, and the size of the window here is 7. Total window size is 7. So this you can refer with a variable SW, indicates the size of the sender window. Okay, initially we would like to send frame 0. So SF is 0 and the next frame which we would like to send is frame number 1. Now once the frame 0 has been sent, this is the frame which has been sent and yet to be acknowledged, and the SN equal to 1 indicates the frame that need to be sent next. So receiver initially is expecting a frame 0, and once it receives the frame 0, it sends an acknowledgement 1 indicating it has received the frame 0, and now I am expecting a frame with a sequence number 1. The sender has received the acknowledgement 1. So what happens is, the 0 which was been initially in the frame sent and acknowledged waiting position, it moves to frame sent as well as acknowledged, and now the frame to be sent and yet to be acknowledged becomes 1, and we will send the frame 1. The next frame to be sent becomes 2. Okay, so SF value becomes 1 and SN becomes 2. Now frame 1 has been transmitted, and since it is a go back and ARQ, before waiting for acknowledgement, we can send the next frames. Like here, we are trying to send the frame 2, and next we are sending a frame 3 before waiting acknowledgement for frame 1. But what happened here is, though frame 1, 2, 3 are transmitted, 2 and 3 are successfully reached to the receiver, frame 1 has been lost. And in the receiver window size, the window size is 1, and the next frame expected to receive is frame 1. So though frame 2 and 3 are successfully received by the receiver, it will not accept the frames 2 and 3 because the RN value is 1. So what happened here is, so you will not get an acknowledgement for frame 2 and frame 3 because the receiver is not accepting the frame 2 and 3. So the frame 1, after it has been sent, it has started a timer, and by the time the timer expires, the frame 1 does not get an acknowledgement because it has been lost in the transmission and not reached to the receiver. So receiver has not generated any acknowledgement for it. So after the timer expire, we will be resending the frame 1, and once frame 1 has been resent successfully, the receiver has received it perfectly, then what happens? Then Rn value will now shift to Rn2, and now since frame 2 has also been not received by the receiver, it does not get acknowledgement, so frame 2 is also resent, and that will be accepted because this time Rn is 2. The third time the frame 3 is sent, this time Rn value is 3, so it will be accepting it, and next the Rn value will move to the 4. So what you could observe in Go Back and ARQ is when frame 1, 2 and 3 are transmitted, and when frame 1 is lost, you have to retransmit not only frame 1 but all the frames that are transmitted after the lost frame. So because of this, frame 1, frame 2 and frame 3 has to be resent. This is what do we mean by a protocol called Go Back and Automatic Repeat Request Protocol and its function. Let us try to find the similarities and the differences between Go Back and ARQ and Stop and Wait ARQ. There is a similarity between Go Back and ARQ and Stop and Wait ARQ. What is that? We can say the Stop and Wait ARQ, which we have discussed initially, is a version of Go Back and ARQ with the value of m, which is the number of bits of used to represent the sequence number is 1. So here for a stop and wait ARQ, we assume m equal to 1. So size of window is 2 power m minus 1, which is 2 power 1 minus 1, which is equal to 1. So here you can send only one frame before you expect the acknowledgement. So in Go Back and ARQ, we said that the addition is modulo 2 power m. In Stop and Wait ARQ, it is 2 power 1, which is equal to 2, same as 2 power m of Go Back and ARQ. Go Back and Automatic Repeat Request simplifies the process at the receiver side. What is happening in Go Back and Automatic Repeat Request? The receiver keeps track of only one variable Rn, and there is no need to have a buffer for out of order frames in case of Go Back and ARQ, because those out of order frames are discarded. For instance, if the receiver Rn number is 2, and if I receive frames 3, 4, 5, all those frames will be discarded, and I will only consider the frame with the sequence number 2. So however, the Go Back and Automatic Repeat Request is inefficient for a noisy link. In a noisy link, the frame has higher probability of damage, which means if only frame 2 was damaged, I have to resend all the frames starting from frame 2. So we have to resend multiple frames. The resending uses up the bandwidth and slows down the transmission. And for the noisy links, there is another mechanism that doesn't need to resend all the n frames when just one frame is damaged. 2, 3, 4, 5, only 2 got damaged. Then why to retransmit 3, 4, 5? Just 2 is sufficient. So to implement this mechanism where only damaged frame is resent, we use a mechanism called Selective Automatic Repeat Request. It is more efficient for noisy links, but here the complexity of the receiver will be a bit more. In Selective Automatic Repeat Request protocol, we are actually trying to resend only the frame that has been got damaged. To implement this Selective Automatic Repeat Request, we are trying to use two windows. One at the sender side called send window, and at the receiver it is called receive window. There are the differences between the send window of the Go Back and Automatic Repeat Request and Selective Repeat ARQ. At the same time, there will be a difference between the Select Repeat and Go Back ARQ in terms of receiver windows. Let us try to understand their major differences. There are differences between the windows in this protocol and the ones in the Go Back and Automatic Repeat. First, the size of send window is smaller when compared with Go Back and ARQ. In Go Back and ARQ, the size of window is 2 power m minus 1. Here, the size of window is 2 power m minus 1. So there is a difference between the two windows sizes. So definitely you could find the sender's window size of Go Back and ARQ is much greater than the selective repeat ARQ. For instance, if I am trying to use m equal to 4 bits to indicate the sequence number. So in case of Go Back and ARQ, the sender window size is 2 power 4, which is 16 minus 1 equal to 15. Whereas, so for Go Back and ARQ, the windows size for m equal to 4 is 15, but same window size m equal to 4, same m equal to 4, the window size in selective repeat is 2 power 4 minus 1. So minus 1 is in the power, so it becomes 2 power 3, 2 cube, which is nothing but 8. So the window size of the selective repeat is smaller than Go Back and automatic repeat request. Second thing is the receiver window size in case of selective repeat ARQ is same as send window. So if your send window size is 2 power 4 minus 1 equal to 2 cube equal to 8, so the receiver window size is also 2 power 4 minus 1, which is equal to 8. So in case of Go Back and automatic repeat request, the size of the receiver window is only 1, but here the receiver window size is same as the sender window size, which is equal to 2 power m minus 1. Now so just as we discussed, if m equal to 4 for our Go Back and ARQ, the sequence number starts from 0 to 2 power m minus 1. So we have sequence numbers ranging from 0 to 15, but for the size of window in case of selective repeat is only 8. So here the sequence number will be 0 to 7. The smaller the window size, actually it is making less efficiency in the pipelining, but the fact is there are only very few duplicate frames. So compared to the Go Back and automatic repeat request, here the number of duplicate frames will be less. And this first major difference, the window size of sender 2 power m minus 1, whereas in that case it is 2 power m minus 1. This is 2 power of m minus 1. So m minus 1 totally is in the power. Okay, so it's almost half of the window size of the Go Back and ARQ. And second, the receiver window size is same as sender window size for selective repeat. And third, they compare to the Go Back and ARQ, the selective repeat ARQ efficiency is comparatively less. But here we need lesser number of, we will have a fewer duplicate frames. Let us try to understand the sender window of selective repeat ARQ. As mentioned, we will take the example of the number of bits to represent the sequence number m equal to 4. So the size of the sender window is m equal to 4, 2 power m minus 1, which is 2 power 4 minus 1, 2 cube. So that is equal to 8. So as discussed in the previous protocols, we have 4 types of blocks in sender window. What are that? Frames already acknowledged, means they have been transmitted and they have received the acknowledgement. Frames sent but yet to receive their acknowledgement. Frames that can be sent next, and frames that cannot be sent until the previous frames are clear. So the second category, frames sent but not acknowledged, means the sender have already sent that particular frame but it has yet to receive the positive acknowledgement. The first frame with which is already the frame has been sent but acknowledgement is awaited, that frame will be represented with a variable SF, and the frame that can be sent next will be indicated with a variable SN. SN indicates the sequence number of the frame that can be sent next. So the size of the window, as we mentioned, it is 2 power m minus 1. So here the size is 8. So here you will start, the sender window starts from 0 and it is up to 8. So total size of the window is 8, out of which 4 frames are already sent and waiting for the acknowledgement, and remaining 4 that are sent. For instance, if I get acknowledgement for frame 0 and frame 1, then 0 and 1 move to the frames already acknowledged, then the SF becomes 2, then the SN, now 4 and 5 can be sent. If not, SN will be 4. If 4 and 5 are also sent, then SN will be replaced with value 6. Okay, so this is how you are trying to use the sender window. The major difference between the selective repeat ARQ window and go back and the automatic repeat ARQ is here the window size is only 8, whereas in that case it would be 2 power m minus 1. So 2 power m is 2 power 4, which is 16 minus 1, 15. And remaining it is same as what you find in the go back and automatic repeat. Coming to the receive window of the selective repeat ARQ, it is totally different from go back and automatic repeat request. First, we have understood that the size of receive window in selective repeat ARQ is same as the size of the sender window, that is 2 power m minus 1. Whereas in case of go back and automatic repeat request, it's only 1. So selective repeat protocol allows as many frames as size of receive window to arrive out of order and kept until there is a set of in order frames to be delivered to the network layer. For instance, I got m equal to 4. So to window size of the receiver is also 2 power 4 minus 1 equal to 8. Let us take these frames as frame 0 to frame 7. For instance, after frame 0, if I receive frame 2, frame 3, frame 4, in case of go back and automatic repeat request, since Rn will be equal to 1, all these 2, 3, 4 which are out of order will be discarded. But in case of selective repeat, the size of the receiver window is same as sender window, and so what happens is though the frames 2, 3, 4 come before frame 1, they are received by the receiver and they are kept in the buffer. So these out of order frames will be received and they kept in the buffer, and all these are set in order before they are delivered to the network layer. So frame 0, frame 2, 3, 4, 5, 6, 7 are arrived. Then frame 1 arrives. Also it will be accepting and rearranging all these 8 frames. Then it will be forwarding to the network layer. Because the size of sender window and receiver window are same, all the frames in the send frame can arrive out of order and be stored until they can be delivered. But what is important? Before they are forwarded to the network layer, they have to be set into order. Now let us look at the receiver window of selective repeat ARQ. As mentioned, the m equal to 4, so the receiver window size is also 2 power m minus 1. Here we are considering m equal to 4. So the receiver window size is 2 power 4 minus 1, which is nothing but 2 cube, which is equal to 8. So here the frame we are starting with frame 3. So the receiver window size is 8. So here 3, 4, 5, 6, 7, 8, 9, 10. So we have the receiver window up to 10 frames. In this, we are actually expecting frame 3 because we have already received up to frame 2. So Rn value is 3, but receiver window size of selective repeat is same as sender window size of selective repeat. So what happened here is, even though we are expecting the next frame 3, but if we are receiving frames 4 to 10, we are going to receive those frames and keep it in and store it for later delivery. So we are keeping them in buffer, but we are not discarding those frames. This is a major difference that happens between the selective repeat ARQ and go back and ARQ. In go back and ARQ, if your Rn is 3, then you are going to discard the remaining frames, but here the remaining frames are a part of the receiver window. So what happens is, even though we get out of order frames from 4 to 10, they are stored for later delivery. This will help in reducing the retransmissions of the frames. Here, in case if any one of the frame is lost, for instance 3 itself is lost, but we have received 4 to 10. In case of go back and ARQ, when 3 frame is lost, we have to retransmit all the frames starting from 3 to 10. But here, when we are losing frame number 3, but we have received the frames from 4 to 10, we have to only retransmit the frame 3 and others can be ignored. Let us look at the design of selective repeat ARQ. Let us look at first at the sender side. Here, the data link layer of the sender is expecting data to be received from the network layer. So once the data is received from the network layer, it is going to make the frames. So the data may be made into more than one frame. The first frame for which is already sent and yet to be acknowledged will be represented with a variable SF. The frame next to be sent will be indicated with a variable SN, and the size of the sender window is 2 power m minus 1. First, once a frame is formed, then the frame will be transmitted through the noisy channel to the receiver. Now the receiver has received the frame, and if there is no error, it will try to extract the data and then deliver the data to the network layer. At the same time, it would try to generate an acknowledgement frame and would like to send to the sender. For instance, what happened here is, whenever the data link layer has sent a frame, first thing it tries to do is, it starts a timer, it keeps a copy of the frame, because we are talking about noisy channels. So before we receive an acknowledgement from the sender, since here we can implement pipelining concept, we can send the next frames before receiving the acknowledgement for the previous frames. In case the timer expires and we don't get the acknowledgement for a particular frame, here we need to only retransmit that particular frame, but not all the frames that have been transmitted after it. That is the major difference. And the process here, the receiver window also, for instance, if it has been expected to receive a frame number 3, but it did not receive that, but it received the next frames 4, 5, 6 like this. Let us assume this is 3, 4, 5, 6. If 3 frame was not received, but we have received 4, 5, 6, we will keep it in order for delivery to the next. And once the frame 3 is received, we'll try to send all the frames. So the important thing that we have to remember in selective repeat ARQ is, the sender window size and the receiver window size is half of 2 power m, where m is number of bits used for sequence number. So 2 power m divided by 2, which is equal to 2 power m minus 1. This will be the window size of the sender as well as the receiver. So next topic we would like to discuss is piggybacking. Before this, so far we have tried to discuss 3 different types of protocols for a noisy channel, namely go back and automatic repeat request, stop and wait automatic repeat request, and selective repeat automatic repeat request. In all these 3 protocols, the data frames are only transmitting in one direction, and the control information such as acknowledgement and negative acknowledgement is transmitting in other direction. Suppose sender A and receiver B. So all the data is flowing from sender A to the receiver B, and the control information such as acknowledgement and negative acknowledgement are moving in the other direction. But in real life, the data frames are normally flowing in both directions. That is from node A to node B and node B to node A. Suppose I am talking to you. So definitely you not only listen to me, you also try to reply to me. When I send you a text, definitely you will also be sending me the text. So the communication or the data flow will be in both directions. So this means when A is sending data to B, so B has to acknowledge. Similarly, when B has to send data to A has to acknowledge. So along with the data, the control information also flows in both the directions. So what we are trying to do is, we are trying to adapt a technique called piggybacking to improve the efficiency of this bidirectional protocols. So bidirectional protocols are those set of protocols in which the communication happens in both directions. Data will travel in the 2 directions. Data travels in the 2 directions. At the same time, control information also flows in the both directions. So we are trying to implement piggybacking technique for bidirectional protocols. When a frame is carrying data from A to B, it can also carry a control information about the arrived frames from B. Suppose A has sent data to B. Now B has to reply to A. So along with data from B to A, B will also try to acknowledge that the data sent by A to B has been received. So what we are trying to do is, when a frame is carrying data from A to B, it can also carry the control information about arrived or lost frames from B, and this can be happen in vice versa direction. So when you are trying to combine data information and control information, that particular process will be referred as piggybacking. Let us try to understand the design of piggybacking in Go Back N Automatic Repeat Request ARQ. So here in piggybacking, control information will flow in both directions along with the data, and it improves the efficiency of bidirectional protocols. So here you will have A and B which are acting both as, so I will talk this device as A and this device as B. So here A is trying to send data to B, so it need to have a sender window. At the same time, A has to receive the data from B, so it has to have a receiver window. And what is the type of protocol we have been discussing? Go Back N ARQ. So size of the sender window is 2 power m minus 1, and receiver window Rn is, so receiver window size is 1. Similarly, the sender window size of B is also 2 power m minus 1, and receiver window size is 1. Let us start from sender device A aspect. So sender A will be receiving the data from network layer. Then the data link layer of A will try to convert the data into frames, then forward the frames, and before sending the frame, it will start the timer and keeps a copy of the frame, because there is a probability of loss or damage to corruption of the frames. So once a frame has been sent, a timer will be set and it will try to send the frames, and these frames will be received by the receiver. If everything is fine, then it will try to extract the data and deliver the data to the network layer. At the same time, it will try to send an acknowledgement for the A. Now A here is acting on behalf as a sender. Now let us look at the concept where B is trying to send the data to A. So B will get the data from the network layer, that will be received by data link layer of B, convert it into frames, and once the frames are made, it will be sent. Immediately the timer will be started and a copy of the frame is being kept, and then we are going to send the frames through a noisy channel. Since it is a go back and automatic repeat request, we have a pipelining concept. Before we receive the acknowledgement for this frame, we can transmit the next frames, right? So what we are trying to do is, B has to send the data to A data frame. At the same time, it has to send the acknowledgement for the frame which it has received from A. So what happen here is, in the frame which is sent by B to A, it contains data information from B. At the same time, a control information which is a positive acknowledgement or negative acknowledgement from B to A, saying that it has received the data from A. The same way, the sender A's frame will also contain both data information as well as the control information, which is acknowledgement or negative acknowledgement. This process of combining the data information along with control information and transmitting the data in bidirectional will be referred as piggybacking. And the main advantage of using piggybacking is it improves the efficiency of the channel. Few important points in regarding to piggybacking in Go Back N ARQ is, each window has two windows. So A is having two windows, that is sender window and the receiver window, and B is also having one send window and one receive window. So both A as well as B also need to use a timer, that was found in the previous slide. An important point about piggybacking is that in both sides we might use same algorithm, because I am using Go Back N ARQ at sender A, I have to use the same algorithm or protocol at sender B. So this algorithm is complicated because it needs to combine two arrival events into one. What are the two arrival events? One is a frame, data frame, and the other arrival event is an acknowledgement frame. Both are to be combined, so there need to be a bit complexity in implementing this particular protocol. Go Back N ARQ protocol with piggybacking. Right. So far we have discussed the different types of flow control protocols for noisy channels and noiseless channels. The next topic we are going to discuss is called as a protocol called HDLC. HDLC stands for High Level Data Link Control, and this is a bit oriented protocol. I hope you people remembered they are variable size framings. We have two types of protocols, bit oriented protocol and character oriented protocol. And here the HDLC is a bit oriented protocol where all the data along with the control information like header and trailer will also be in form of bits. And this is a bit oriented protocol used for communication over point to point and multi-point links. What do we mean by point to point? A dedicated link between the two devices, and a multi-point link, a link which is shared between number of devices. So HDLC, which is a bit oriented protocol, is also implementing automatic repeat request mechanisms. Okay, and HDLC provides two common transfer modes that can be used in different configurations. So the HDLC which we are talking so far can be implemented in two different configurations. What are that? First one is called normal response mode, and second one is called as asynchronous balance mode. Let us look at what do you mean by normal response mode and asynchronous balance mode. Let us look at the first type of transfer mode of HDLC, which we are referring it as HDLC normal response mode. A HDLC normal response mode is a mode in which the station configuration is unbalanced. We have one primary station and multiple secondary stations depending on the type of link. If it is a point-to-point link, we will have only one secondary station. If we are having a multi-point link, we are going to have multiple secondary stations. But in normal response mode, we are referring it as unbalanced because here the primary station can send the commands and the secondary stations can send only the responses. Means primary cannot send responses, at the same time secondary cannot send the commands. Whether it is point to point or multi-point, the role of primary is to send the commands and the role of secondary is to send the responses. So the normal response mode is used for both point to point and multi-point links. And remember, in normal response mode, the primary sends the commands and secondary just use the response. That is the reason why it is called unbalanced or normal response mode. The second type of transfer mode for HDLC is referred as HDLC asynchronous balance mode. In asynchronous balance mode, the configuration is balanced. Why we are calling the configuration is balanced is, here we are not having anything like primary station or secondary station. Each station will be referred as a peer because each station can send the commands, at the same time each station can send the responses. So here you have two stations which are connected by a point-to-point link, and each station will be functioning as primary as well as the secondary. And this is the most common mode which you are finding in HDLC implementation. So first, HDLC is a bit oriented protocol, and it operates in two transfer modes, which is normal response mode and second one is asynchronous balance mode. In normal response mode, we have primary which sends the commands and secondary which just use the responses, and we can operate therein both point to point and multi-point. But for asynchronous balance mode, this is the balanced configuration mode where each station acts as both primary and secondary, and each station can send command or response. But here we can implement only in point to point link. Now let us summarize for today's topics that we have discussed in today's class. We have started our discussion with Go Back N automatic repeat request, where the frames will be transmitted using a concept of pipelining, and more than one frame can be sent before receiving an acknowledgement. But we have to keep the frames till we receive the positive acknowledgement, and we have to start the timer. If any of the frames doesn't receive, we are going to retransmit the frame. The sender window size of Go Back N automatic repeat request is 2 power m minus 1, where m equals the sequence number of bits used for the sequence number. But the receiver window size of Go Back N automatic repeat request is only 1. The mechanism that is implemented in Go Back N automatic repeat request is when you are sending multiple frames, but if one of the previous frame got damaged, then all the frames followed by it along with it should be retransmitted, because the receiver will be receiving only an expected frame, and if it receives any other frame other than the expected frame, that will be discarded. To overcome this problem, we are implementing the next protocol called Selective Repeat ARQ, in which both sender and receiver are using same window size of 2 power m minus 1. Here the window size is half of the 2 power m, but what happens is, even if the frames which are expected comes in out of order, instead of being discarded, we'll try to store them until all the frames are arrived, and then we try to rearrange before sending to the network layer. So the drawback which we have of retransmission of multiple frames, even though only one frame is damaged, in case of Go Back and ARQ, will be overcome in Selective Repeat ARQ, where we are going to only retransmit the frame that has been damaged. And the last frame we have discussed for today class was about HDLC. What is the HDLC protocol? What are the different configurations in which HDLC is operated? So in our next class, we will be discussing about multiple access and various types of protocols used for the multiple access. Hope you have understood this very important function called flow control of data link layer. Let's meet in the next class, and we will be discussing about multiple channel protocols.